Hey everyone, and welcome. Today, we're diving deep into the one thing that connects literally everything in the universe: matter. Seriously, from the farthest star you can see to the phone you might be holding right now, we're going to break down the fundamental rules that build our reality. So let me ask you this. It sounds like a riddle, right? What could those three things possibly have in common? Well, the answer is actually pretty simple. They're all made of matter. That's it. The chair you're sitting on, the air you're breathing, it's all built from the same basic stuff, just arranged in a bunch of different, amazing ways. So here's our game plan. First, we'll get the big picture on what matter even is. Then we're going to zoom way into the atomic world. After that, we'll check out the ultimate blueprint for all the elements, see how they change and react, and finally, bring it all back to the chemistry that's happening around you every single day. All right, let's jump right in with the most basic question of all. When you look around, what are you actually seeing? Well, it all kicks off with one simple definition. There it is, the textbook definition. Basically, if it has weight and it takes up room, it's matter. It's a simple rule, but it unites everything from a tiny grain of sand to the biggest star in the galaxy. But, as you're about to see, matter comes in some very different flavors. So what's the difference between a block of ice, a glass of water, and the steam coming off a kettle? Just one thing: energy. In a solid, particles are locked in tight. Not much energy, lots of attraction. But if you add some heat, some energy, you get a liquid. Now the particles can slide past each other. Crank up the energy even more, and boom, you've got a gas, where super energized particles are just flying all over the place with almost no attraction to each other. But wait, solid, liquid, and gas. That's not the whole story. Not even close. The most common state of matter in the entire universe is actually plasma. That's the super hot stuff that stars are made of. And on the total opposite end of the spectrum, if you cool things down to the coldest temperature imaginable, you can create a fifth state, the super weird Bose-Einstein condensate, where atoms basically merge and act like one single giant superatom. Wild, right? We can also sort matter by what it's made of. You have pure substances. Think of a grain of salt or sugar. It's made of only one thing, through and through. Then you have mixtures, like the air you're breathing. It's just a big jumble of different gases, like nitrogen and oxygen, all mixed together, but not actually connected. Okay, so we've sorted matter on the big scale. Now let's zoom in. Let's zoom way in, past what any microscope could ever hope to see, to find the one tiny unit that builds everything else. And here it is. Meet the atom. For the longest time, we thought this was it. The smallest possible piece of anything, the final stop. Now we know it's made of even smaller bits, but it's still the fundamental building block for every single chemical element. Our picture of the atom didn't just appear overnight. It was a real journey. We started back in the 1800s with Dalton, who thought atoms were just tiny, solid balls. Then J.J. Thomson found the electron, and he came up with this plum pudding idea. But then Ernest Rutherford's famous gold foil experiment completely changed the game, revealing a tiny, dense nucleus at the center. And finally, Niels Bohr gave us the model most of us learned in school, with electrons orbiting that nucleus in specific energy levels. So every atom has three key players. You've got the positive protons and the neutral neutrons hanging out in the nucleus, the core, and then zipping around that core are the tiny negative electrons. It's the number of protons that decides what element you're looking at, and it's the beautiful dance between all three of these particles that makes all of chemistry happen. Okay, so we've got atoms and they make up elements. But there are over 100 different elements out there. How in the world do you keep track of all of them? Well, luckily for us, chemists came up with an incredibly powerful tool to organize everything. I know, it might look a little intimidating hanging on a classroom wall, but the periodic table isn't just a chart. Think of it more like a map, or the ultimate cheat sheet for all of chemistry. It brilliantly organizes all the elements in a way that reveals these deep patterns in how they behave, and even lets us predict what they'll do next. It's honestly one of the greatest scientific achievements ever. So how does this amazing map work? Well, thanks to a guy named Henry Moseley, it's all arranged by atomic number, which is just the number of protons an atom has. But the real magic is in the vertical columns, the groups. Elements in the same group, like these super reactive halogens or these super chill noble gases, have similar chemical personalities. Why? Because their electrons are arranged in a similar way.
And this layout lets us predict all sorts of things, like how big an atom is. Now, as you go down a group, atoms get bigger. That makes sense, right? You're adding more layers of electrons. But here's the crazy part. As you move from left to right across a row, atoms actually get smaller. How is that possible? Well, you're adding more protons to the nucleus, which creates a stronger positive charge that pulls all those electron shells in just a little bit tighter. It's these kinds of hidden patterns that make the table so incredibly useful.
Okay, we know what matter is, we know what it's made of, and we know how it's all organized. So now we get to the really exciting part. How does it all interact and change and create new things? You see, at its heart, chemistry is all about reactions. Sometimes you combine things, like when hydrogen and oxygen get together to make water. Sometimes you break things down or decompose them. Sometimes elements swap places with each other. But a whole lot of the most important reactions, called redox reactions, are all about one simple thing: an electron hopping from one atom to another. And here's the thing, every single chemical reaction involves energy. It either releases it or absorbs it. So exothermic reactions, like a campfire, give off energy. You can feel the heat. But endothermic reactions, like those instant ice packs you shake up, actually get cold because they have to suck in heat from everything around them just to make the reaction happen. So why does all this matter? Because these fundamental rules aren't just for some fancy lad. They are happening all around you, and even inside of you every single second of every single day. I bet you've heard of the pH scale. It's the perfect example of everyday chemistry. It measures how acidic or basic something is, from lemon juice to drain cleaner. And you know what it's really doing? It's just counting the concentration of hydrogen ions. That's it. And this is why that scale is so incredibly important. Your body has to keep its pH in this ridiculously narrow range, between about 7 and 7.8, just to stay alive. Every vital process, from carrying oxygen in your blood to digesting your lunch, depends on that perfect chemical balance. It's like a constant invisible tightrope walk. And if we're gonna talk about life, we have to talk about carbon. Carbon has this amazing superpower called catenation. It's this incredible talent for linking up with other carbon atoms to form long, stable chains and rings. This one property is what makes it the perfect backbone for the millions and millions of complex molecules that make you, me, and every living thing on this planet possible. Let's end with something we all have at home: soap. Making it is a classic chemical reaction, but have you ever noticed how regular soap doesn't work so well in hard water? That's chemistry in action. The soap reacts with minerals in the water, like calcium, and just stops working. So what did chemists do? They invented detergents, specially designed molecules that are engineered to completely ignore those minerals and get the cleaning job done no matter what. It's a perfect example of using chemistry to solve a real-world problem. So there you have it. From the different states of matter all the way to the elegant layout of the periodic table, we've seen that the universe isn't just random chaos. It's governed by a set of beautiful, predictable rules. And once you understand those rules, you have the power to not just watch the world, but to actually build with it. Which leaves us with a pretty exciting question. Now that we know the rules of the game, what incredible new materials will we build next?